So we're gonna do lecture 11.6, periodic input frequency response. And what we're doing in this lecture is kind of gluing together several concepts that we've learned along the way. Really the primary ones being the Fourier series, the frequency response, and superposition, okay? So these are the sort of three concepts that we're going to bring together in this lecture. And it's really useful way to analyze systems and to think about systems is in the way that we're going to talk about them in this lecture. And that's, I think, an important thing to take forward from system dynamics. This is actually the last lecture on system dynamics proper that we're going to do. System controls is what we'll start to do next week after the exam. All right, so lecture 11.6, periodic input frequency response. Let a system H have a periodic input U represented by a Fourier series. The Fourier series has amplitude components A, N. I used the script A here. And we've got frequency components, integer multiples of the fundamental frequency, omega 1. And we've got phase components as well. And then we've got our zero frequency or DC offset component here. So good old-fashioned Fourier series with a sign. That's one way to represent a Fourier series in the trigonometric form. So say we've got this, and we are going to use this now, not just as here's a signal, let's break it down into components. We're going to actually use this to go into a system as the input to our system, okay? So that's kind of one of the things that's new here is that we're taking this Fourier series and we're putting it into a system as the input. See what happens. So the nth harmonic, we're just going to take the nth harmonic component here. We would have U sub n of t being equal to script A n sine n omega 1 t plus phi n, which from equation 1137, which is the big boxed equation that we looked at before. I mean, this is the one that we did outside that lecture, where we had the final boxed equation being that when you put in a sinusoid, you get out a sinusoid with the new amplitude and a new phase, according to the following relationship. So y sub n equals script A sub n. So the input amplitude comes to the output amplitude, but it gets scaled now by the magnitude of the frequency response function at the frequency of that input, which is n omega 1 times, once again, it's a sinusoid at the same frequency as the input, plus the input phase, phi n, plus the phase of the frequency response function evaluated at the frequency n omega 1. Okay? So this is our good old-fashioned put in a sinusoid, get out a sinusoid, scale the input amplitude by, so there's our input amplitude again, scale it by the magnitude of the frequency response function. And then the phase comes into the output, but we add to the phase of the frequency response function. Yeah?
So the angle symbol is a phase shift symbol?
Yes, exactly. So this is the phase symbol. Yes. Sometimes also called the angle. Great. So we broke down this periodic input into a bunch of sinusoids, Now we found what the output is for each of the sinusoids. And now we're going to apply the principle of superposition, which said a few things, the principle of superposition. One of the things it said was if you have an input that is comprised of a sum to a linear system, so if you have an input to a linear system that is a sum of terms, you can take each term separately, find the output for that term, and for each term, and then sum those outputs to get the total output. And that's what we're going to do here. So we'll focus on the second term first, the sum. We're essentially just summing up all of these y sub n's here. So y sub n from this expression above. And what we get then is the total output if you put all of those sine components in, or if you put in that periodic function. The DC term here, this was the input, this part, gets scaled by the zero frequency frequency response function evaluation. So that's the output. So that's our solution for a periodic input that's the forced response of a periodic input. So expressed in terms of a Fourier series, which is, a pretty good way to go about doing it. So pretty nice solution for us. We also have a Fourier series representation in this complex exponential form, right? Like equation 1147, and we tend to introduce the sinusoidal one or the trigonometric form first because it's very obviously sinusoids, right? But the Fourier series expressed in terms of the complex exponential is also a sinusoid, just expressed mathematically a little bit differently. So if that's our input, the corresponding output is this, where instead of needing to use the magnitude and the phase separately, we can just use the complex value of h, which is kind of nice. And the principle of superposition yields this as the solution. Pretty nice mathematically to do it in this complex form, but conceptually the trigonometric form is the one that tends to be the one that we can hold on to a little bit better because it's sinusoidal. It's very clearly sinusoidal. You can see those sine cosine terms show up in there. So 1146, so this first trigonometric form, or the trigonometric form of the solution, and the second, the complex form, tell us that for a periodic input, we obtain a periodic output with each harmonic omega n amplitude scaled by the magnitude of the frequency response function at that frequency, and the phase offset by the phase of the frequency response function at that frequency. So as a result, the response will usually undergo significant distortion called phase distortion. So you can imagine, you had like some input function that had all these different components associated with it, right? So maybe a stronger third harmonic and a stronger seventh harmonic and a stronger 10th harmonic or whatever. And then it goes in to this system, and each of those components gets scaled a little bit differently. And each of the phases gets shifted a little bit differently. So when you sum up those results, it often, the function doesn't come out looking like it did when it went in, okay? It looks different. So that periodic function might have looked like a triangle way of going in, and when it comes out of the system, it might look like something with like wiggles. It'll be periodic, but it might look like that or something. Like it could look very different than it did going in. Oftentimes, it looks more rounded off, okay, than it does going in, because many frequency response functions filter out high frequency components, and sharp corners have a lot of high frequency components in them. Okay. the system H can be considered to filter the input by amplifying and suppressing different harmonics. This concept of filtering is actually a very important way of conceiving of a dynamic system, as filtering different frequency components and distorting that input in the frequency domain. So this is why systems not intended to be used as such are still sometimes called filters. So some dynamic systems are specifically built to be filters, right? Like you have talked about, like electronic circuits that were built to filter a signal electronically. Okay, that's nice. But when you talk to folks who are like EE folks especially, you're going to hear them talk about filters in a much broader sense. It pretty much, for them, any dynamic system is a filter. So you're going to hear that language out there in the world, and even when I'm feeling particularly edgy, I might even use it every once in a while. Filter. Sometimes I pretend like I'm an EE person, like I'm super cool or something. Yeah. So this way of thinking about systems is very useful to the study of vibrations, acoustics, measurement, and electronics. We're going to circle back to that measurements concept after we look at this visualization. So anytime we've got these periodic signals that are going to be going through a dynamic system, this is very useful. And even when they're aperiodic, you can use the Fourier transform in a similar way to conceptualize this filtering concept. So all this can be visualized via a Bode plot, which is a significant aspect of the Bode plot's analytic power. An example of such a visualization is illustrated in figure 11.9. So what we've got going on in this figure is an input line spectrum. So input line spectrum. And it's got, our usual harmonics that have different amplitudes and phases, okay, going in. And this is essentially like a graphical representation of the Fourier series, right? Where we know these are all just summed up at different frequencies and added together. Or summed and added would be redundant, but I think you got my drift. So we've got these input amplitudes and phases, and we have this frequency response function of the system. So it says frequency response of the system, but we also say this is the Bode plot, right? The Bode plot of the system. So this is just for some, once again, so this is the input line spectrum of some input function. So it could be like a sawtooth or something like that. And then it's going to go through some system. This is an example. Not every Bode plot looks like this, obviously, but it looks like a second order Bode plot. And for a second order Bode plot, the magnitude starts off around 1, and then it is going to come up and have a little peak there. So there's some resonance happening, and then it's going to go down to, this is plotted. This is close to a Bode plot. This is not a log magnitude. You might notice that this goes off to 0 instead of going off to negative infinity with the dB scale. So that's one difference with the Bode plot. And then the phase has this phase shift that starts off at 0 and goes to some negative number. We're looking at qualitative changes here, not quantitative. So that's what we'll do first. And then we've got this output. So the line spectrum of the output, okay? So this is all the output. And let's trace and see how each of these components gets transformed through the system. So the input magnitude, let's take like the first harmonic here. And let's look at that amplitude, AN. it's going to multiply if you just go down in frequency here, or down at the same frequency. You're going to multiply that by something about 1-ish. So it's not going to change it by much, okay? It's just going to stay about the same. And you keep going down, and this thing has that as the output magnitude. The output magnitude being the product of the magnitude of the frequency response function and the input amplitude. Yeah?
So is this logarithmic but not in dB scale, or is it not?
This is not logarithmic. This scaling is not logarithmic.
Is that why we're multiplying instead of adding?
Well, we're always going to be multiplying. So if you had this in log and you had this in log, then you could add them. Yes. So if they're both logarithmic, then you could add them.
That's what we're doing on Monday, right? We had them in both in log.
So yeah, so what we did on Monday was we had two different components of a Bode plot, and they were both log, so we added them. Precisely. So good. It's good not to get that confused. Yeah. So this one we're leaving it in linear scale instead of log. So in the magnitude, so that we can just do a multiplication. Bang bang, get the output. This is not something we're necessarily going to do graphically, but it's something that we're going to just conceptualize as being something that we're going to do. So we conceptualize it as being, oh, okay, this gets multiplied by that to give us that. And this, so like the second, let's actually take the third, because the third happens like right on the resonance pretty much. So the third one gets multiplied by that peak value, so it's going to increase in size. So notice the profile here, it has this early peak and it goes down. This third harmonic is going to get amplified in the output because of the resonance. So you see that third harmonic is higher on the output. So it's taking on the shape. So it has some of its original shape, but it's also taking on the shape of this frequency response function. And as you go to higher frequencies, the frequency response function magnitude drops off, right? So down here, like the 7th harmonic, it gets multiplied by a number that's relatively small. So we were expecting to see this shrink in size, 7th harmonic shrink in size, and sure enough, it does. Great. So let's look at the phase too. The phase is usually less exciting, but it's good to keep in mind that there's also this direct phase distortion that's happening too. The phase distortion, notice that the frequency components have opposite sign here. They're going every other. Say it's like plus 90, minus 90, plus 90, minus 90, okay, in the input. Well, those are all going to get shifted negative, right? They're going to sum with this phase. So they're all going to get shifted negative along this sort of curve. So what we're going to see in the output is that plus 90, minus 90 all moving down to negative numbers. So like, I don't know, negative 135, negative 60, something. And back and forth as we go.
And those ones are added?
And those ones are added, yeah. So this is the input phase plus the phase of the frequency response function. So this spectrum represents a periodic signal that's going to look a lot different than the input, right? And so that's first of all, it's an important fact to understand that that's going to happen, and what the implications are for different applications can be significant. So let's imagine one dynamic system. So one that's near and dear to my heart is a measurement dynamic system. Okay, so when we measure anything, our measurement instrument or our sensor has its own system dynamics associated with it. So it has a Bode plot. It could be second order, but a lot of them are. So say like a force sensor or a pressure sensor. a lot of times could be a second order sensor. So if you're just going to be taking measurements very slowly, no big deal. Say you've got a big steel plate and you're going to just drive a truck onto it and you're going to weigh it through these force sensors. Well, what you do is you drive a truck onto it, you park it, let the scale settle down for a minute, and then once it gets to the final value, you're like, okay, that's the weight of this truck. Good. But say you had a plate that was supposed to be measuring maybe it was trying to characterize how a vehicle is going to wear on a surface or a roadway or whatever, and you wanted to use a force sensor plate to drive vehicles over going at highway speed or something like that. So you're going to have the vehicle hit the plate, drive over the plate at a pretty fast rate. So maybe the force looks something like it's 0, and then you have this like super high spike as the car first starts to come into contact, and then it fades out like this or something. And that's the force profile you're trying to measure. Well, and maybe there's a whole train of them, so it's periodic, but you can also think of this as being aperiodic. So say that's your force profile. If that goes in, and let's say it's periodic just for the sake of argument for this periodic signal. So say you've got a bunch of cars coming over and over again, loading this thing. If this is your force profile that goes in, it has a frequency, it has a line spectrum that's going to include some pretty high frequency stuff, okay? So anytime you've got these sharp corners, you've got some high frequency stuff in it. And once you put that through your second order dynamic system, if this, so there's this low frequency region down here where the magnitude is pretty flat and the phase shift is pretty flat. So this is very common for most dynamic systems, especially measurement systems. It's pretty flat, at low frequency, and that's where you're not going to distort stuff much. Once you get into the higher frequency stuff, you're going to start distorting. So if, say this was the line spectrum of your input, it's gonna come out looking like a mess. Okay, it'll look like this would probably look like that, and you probably wouldn't have the second wiggle there. It would probably look more like this. It would just like all of this characteristic up here we wouldn't even see it. So you would look at your data and you'd be like, oh, it just gives us a little hump whenever a car hits it. But you're missing a whole lot of the signal here. It just got filtered out by your measurement device. So what are your options? If you want to measure this, you have to change your measurement system to shift all of this stuff, the resonance, and then the high frequency roll off here. You have to shift it to higher frequency, okay? So you need a wider band for your measurement frequencies. So now we've got out here, because anything that's higher than this is probably getting smaller and smaller and smaller in the line spectrum, okay? So make it flat up to, say, here, then let yourself have that hump and that roll off, which you can do by increasing the natural frequency of the device, for instance. It's one way to do it. So make it stiffer or reduce the mass, something like that. And then you have this input that would not get nearly as distorted, okay? So then your fidelity to the original signal might look more like this. and you'd be a lot better off. Your measurement would be a lot more accurate for the system that you're trying to measure, or the input signal you're trying to measure. So knowing when you might have this happen is really important. Like, so you're saying, okay, what is my approximate input profile? I mean, there's a bit of a chicken and egg problem here, right, that you often run into in design, because you don't know what it looks like before you measure it, so you're measuring it to see what it looks like, but you don't know how to measure it until you know what it's going to look like. It's a bit of a troublesome situation. But what you can do is you can say, okay, let's just reason our way to, like, approximately, what do we think this profile is going to look like? Like, what do you think the max is going to be? I know how long that tire is going to be in contact with it when it rolls over. So let's say that it, like, peaks here and it has this sort of triangle shape to it. If that's what the shape was, what would I need for my measurement system, frequency response? Then try it, see if it seems like you're getting a good readout. Now, another thing you can try is, you never know. There could be, it's rare, but there are situations where you're going to have an input signal that's like got some stray high component, high magnitude, way out at some high frequency. That's possible in your measurement signal. But you're going to have to just at some point say, I'm going to ignore any frequencies higher than this cutoff, and you won't capture them in your measurement. So they could be there. You can't rule them out in your measurement, but you also can't move this out indefinitely. It's going to, every measurement system's got to have a roll off somewhere. So, yeah.
Is that kind of down to like the price of the tool?
Yeah. So that a lot of times it's an economic trade-off where you're like, what do I really need from this measurement? Maybe you want to characterize it to find out, maybe you just want to sense like when something goes over it. In which case, maybe just a little bump is fine. But if you want like fidelity to what the actual profile looks like, you're going to need to get typically a more expensive sensor. It's not always more expensive, but frequently it is. If you need this range, this dynamic range of your measurement device to go up to those higher frequencies, oftentimes it's more expensive to do so. Sometimes it's just a choice of it can be a trade-off sometimes in like noise accuracy, or like there are a few other trade-offs sometimes that you have, and it's not always cost, but cost is frequently the thing that you have to play with. So you got to make an optimization choice based on what you want to measure and what kind of information you're trying to get out, what your input signal probably is. Yeah. Okay, so that is this phase distortion discussion. Any questions on that?